Hello viewers, in today's lecture we will discuss some numerical methods to find roots of nonlinear equations in one variable. In previous lecture we discussed the simple method of successive bisection, where we were not using any approximation for the function. However, the function was calculated and the sign of function was used to decide the interval of interest. The convergence of method was depending on the width of initial guess or initial range. If you take two functions with same initial range, the method will likely converge in same number of iterations, as we are not using any approximation for the function. To improve the bisection method, a function approximation near the root is introduced in false position method. The function near the root is approximated by a line in this method. The line which passes through x axis will give us the next approximate root. Therefore, this method is called the method of linear interpolation. Similar to bisection method, we start with initial interval. That means, we will take two values of x, x1 and x2, which contains the root. We will calculate the value of function at these two x values. The values are correspondingly y1 and y2. This will give us 2 points on the function graph. These 2 points will be x1 y1 and x2 y2. Near the root, we can assume that the line passing through these 2 points will approximate the function. Therefore, the line passing through these 2 points will cross the x axis at some x value, say x3. At this value, the function should be 0, but if it is approximation, we will get next approximation for the root. So, we will just use this approximation and find out the expression for next approximate root by using linear approximation. Consider the 2 points, as we have already discussed, x1 y1 and x2 y2. These are 2 points, and we just write the equation of line. As you can see on your screen, the equation of line, we will write the equation of line passing through these 2 points. Now, this line will cross x axis at, say, x is equal to x3, and since at x axis the value of y, the corresponding value of y, that means y is equal to y3, it will be equal to 0. So, if you substitute x is equal to x3 and y is equal to 0 in the above equation of line, you will get the expression. You can see on your screen, these expressions will be there, and after simplifying you will get the expression for next approximate root. The next approximate root after simplification is given by equation 1. So, we will get the value x3, which is next approximate root, from the two initial approximate values x1 and x2 by using this equation. The stopping criteria is same as we have discussed in the successive bisection method. Of course, the selection of interval of interest will be same as the successive bisection method, and we will illustrate this in figure 1 and 2. You can see in figure 1, we have the points x1 y1 and x2 y2. These are 2 points, and we draw a line passing through these 2 points. The line is crossing the x axis at x3, and you can see now the interval of our interest will be x3 x2. In next figure, you can see another function, and for this function we have these 2 points x1 y1 x2 y2, and we draw a line. This line crosses x axis at x3, and now you can see that the interval of interest is that interval which includes the root, that means which includes the function the x value where the function is 0. We can also discuss or we can also draw the same formula by using geometrical interpretation. Now, consider the function graph and take 2 points on the function graph, that is suppose point A and B, these are 2 points on the function graph, and the corresponding values as we have discussed are x 1 y 1 and x 2 y 2. The straight line passing through these 2 points will cross the x axis at point P, and there the value of x is suppose x 3. Now, if we construct a triangle from these points, the triangle will have point A and B, and of course, the point P where the line crosses x axis, and we just draw the perpendiculars and get a point D, which will give us a right angle triangle ABD. So, now we have two triangles ABD and ACP, which are similar triangles. You can see in the figure 3 on your screen, there are two triangles ABD and ACP. These two triangles are similar triangles. We can use the property of similar triangles. The property used is that if the triangles are similar triangles, the ratio of corresponding arms will be equal. So, we will write this property, and here we will have the equation Cp upon dB is equal to AC upon AD, the corresponding ratio of corresponding arms, and the value of these can be obtained from geometry. Cp is equal to x 3 minus x 1, dB is equal to x 2 minus x 1. Similarly, AC is equal to value of y 1, that means modulus of y 1, and AD is sum of value of y 1 and y 2. Using these values, we will get the expression for x 3. As you can see on your screen, after simplification, we will get the value of x 3 as given in equation 2. The equation 1 and 2 are almost similar. The only difference is that here we have only the values, that means the absolute values of the function. Now, with this information, we can write the algorithm for the method. You can see on your screen the algorithm for the method. The algorithm is very much similar to the successive bisection algorithm. Here also we read the initial guess x 1 and x 2 and the allowed error epsilon. Now, we calculate the function y 1 and y 2 and just calculate the product p, which is the product of y 1 and y 2. If this product is greater than 0, that means the root is not included in this interval and we will come out of the procedure. If the product is less than 0, that means root is included, then we will continue with the procedure and we will calculate the next approximate root by using equation 1. So, we have written the expression for equation 1 in step 4. There we get calculate x 3 and we calculate corresponding y 3. Now, we calculate the product p, which is y 1 into y 3, and just select the interval as we have done in the successive bisection method. So, if p is less than 0, then we select the interval x 1 and x 3, and if p is greater than 0, then we select the interval x 2 and x 3. After this, in step 6, we calculate the relative error by using the recently calculated root and the previous root, we calculate the relative error, and then we reassign the newly calculated root to the previous root. We check the error. If this absolute error is greater than epsilon, then we repeat the whole procedure. Going to step 4, we will recalculate the point of intersection, that means the point where the line is crossing x axis, and calculating the next value of root. So, we will continue till the error becomes less than epsilon. The false position method is having linear convergence. A closer examination of working of the method will see that the one end of the interval becomes fixed when we approach the root, and that gives us a linear convergence of false position method. Now, in false position method, we have something better than successive bisection method. We have a linear interpolation approximation for the function, and of course, the stopping criteria and initial guess are similar to the bisection method. The convergence, of course, as we have discussed, is linear. A better method is Newton-Raphson method. and in this method we will have better convergence, and of course, we will have only one initial approximation to start the method. This is better than successive bisection as well as false position method, and the initial approximation is suppose x 0 and corresponding value is suppose y 0. So, that gives us a point p x 0 y 0 on the function graph. Now, we approximate that the function will be rather the function can be approximated by a tangent at this point if we are very close to root. So, close to root we approximate the function by a tangent at this point, which is obtained from the initial case. So, this tangent which is drawn at point x 0 y 0 will cross the x axis, and that will give us the new approximate root. We can draw the expression for new approximate root by using analytical method or by using geometrical method. So, first we will discuss the analytical method, and here suppose the exact root is a and approximate root is suppose x 0, and the difference between these two is suppose h. So, we can write a is equal to x 0 plus h. Since at exact root the function value will be 0, therefore, the function at x 0 plus h should be 0. So, using this expression f x 0 plus h is equal to 0, we can use Taylor series expansion for a small value of h. If the correction is small, we can expand f x 0 plus h by using Taylor series method. So, Taylor series expansion gives us the expansion of x 0 plus h around x 0. Now, if h is small, we can neglect the h square and higher order terms in the expansion, and that gives us the correction term h in Newton-Raphson method given by equation 1. So, if you use this equation 1 in our approximation, we will get the next approximate root x 1, which is equal to x 0 plus h by substituting h is equal to minus f x 0 divided by f dash x 0 from equation 1. So, equation 2 gives us the next approximate root x 1. We can also see the geometrical interpretation. Here what we have the function graph, you can see on your screen the function graph, and we have the point P on the function graph. At point P, what we do, we draw a tangent, and this tangent crosses the x axis at point M, where the value of x is suppose x 1. Therefore, we have a triangle P M N, and in this triangle the value of tangent theta can be calculated, that will be equal to P n upon M n. So, from this we get the value of tangent theta, because we know P n is equal to f x 0, that is y 0, and we know M n is the difference between the initial approximation and next approximation, and we call it correction term, that is h. So, you can see here, you can see that from this triangle we have tangent theta, which is M n P n upon M n, that is f x 0 upon x 0 minus x 1, and tangent theta of course is slope of the curve at point x 0. So, we can write tangent theta is equal to f dash x 0, slope of the curve, and using these two values of tangent theta, one tangent theta f x 0 upon x 0 minus x 1 and other tangent theta is equal to f dash x 0, we can obtain the value of h, and that is f x 0 upon f dash x 0, very much or rather exactly same as we have done from the analytical expression. Now, the criteria, stopping criteria or rather the convergence criteria for the Newton-Raphson method is that h should be less than 1 near the root. That means f dash x 0 should be greater than f x 0. The relative error, of course, as similar to the false position method, will be calculated from the two closest root, two successive roots, and then we will put the condition that if ER becomes less than epsilon, this allowed error, we will stop. We can write the algorithm, you can see on your screen the algorithm. Here we start with the initial value x 0 and we read of course the allowed error epsilon, and then what we do, we calculate the correction term h, which is equal to minus f x 0 upon f dash x 0. We get the next approximate root by using the expression x 1 is equal to x 0 plus h, and then using the x 0 and h, what x 1 and h, rather newly calculated value x 1 and h, we calculate the relative error. We check the relative error. If the relative error is greater than epsilon, then we say that the newly calculated root is now initial approximation. So, we set x 0 is equal to x 1 and we go to step 2 and recalculate the whole procedure. We continue this iterative procedure till the error becomes less than epsilon. So, it is similar to the other iterative procedures. The convergence of Newton-Raphson method is much better than the false position method. The convergence factor is 2 and the convergence analysis gives us the equation 3, where we have the ratio of 2 consecutive errors, and this gives us the convergence factor 2. We will discuss the convergence calculation of convergence of iterative methods in next lecture, and the truncation error, which is inherent error in the Newton-Raphson method, is given by equation 4. Here the m is maximum value of the second order derivative of function near the root. Now, you can see in Newton-Raphson method we have the quadratic convergence, that means the order of convergence is 2, which is much better than the false position method. However, you can see one more thing, that here we have to calculate 2 functions for every correction term. So, the computational work is slightly greater than the false position method, where we calculate only one function value and use that function value to redefine the interval of interest. A middle method, that means a method which provides a alternative for both false position method and Newton-Raphson method, is secant method. The convergence of secant method is slightly better than false position method, or rather you can say much better than false position method and slightly less than the Newton-Raphson method. However, the computational efforts are less than Newton-Raphson method and almost equal to the false position method. So, the secant method is you can see that it is extension of false position method. We again start with the initial interval including the root as the initial approximation, and the next approximate root is calculated by using linear interpolation as we are doing in the false position method. However, the difference in secant method and false position method is that the next approximate root or the next interval of interest is not decided by the sign of the function. As we were doing in the false position method, we were deciding the next interval of interest by using the sign of the function. The value of the function was calculated at x 1 and x 3, and we were getting the product of these two, and if the product is less than 0, then we are calculating one interval, otherwise we are calculating the other interval. Here what we do, we take the 2 recent value of approximate root as interval of interest. So, this is rather simpler method than false position method. The burden of logic calculating the interval of interest is avoided in secant method. So, as we have done in the false position method, the approximation used for the function is linear approximation. Suppose after few iterations we get 2 successive roots as x n minus 1 and x n. The corresponding value of y calculated at these 2 x values are suppose y n minus 1 and y n. That means, we are getting the 2 points on the function graph. These are x n minus 1, y n minus 1 and x n y n. As we have defined, we will use the linear interpolation. That means, we will approximate the function by a line passing through these 2 points. So, we again write the equation of line. You can see the equation of line on your screen passing through these 2 points. Now, this line will cross the x axis at some point, and this point is the next approximate root, say x n plus 1. So, at this point the value of function will be 0. So, what we do, we substitute x is equal to x n plus 1 and corresponding y n plus 1 is equal to 0, and that gives us equation 5 for next approximate root. You can see in figure 5 the working of secant method. We have x 0, x 1, these are initial values x 0 and x 1, and what we do is we just draw a secant, that means a line passing through these 2 points, and this line passes through x 2. Next approximation, what we do, we take x 1 and x 2 as the 2 points, and through these 2 points we draw a line, and this line passes through x 3. You can see on your screen this line is passing through x 3. This gives us the next approximate root x 3. Now we discard x 1 also, and we take x 2 and x 3 as our 2 points to approximate the next root. So, we continue in this process. This is how the method will work. The stopping criteria is same as in false position method. We will calculate the relative error in 2 successive approximations, and we will compare it with some small number allowed error, and if this error is less than epsilon, then we will stop, otherwise we will continue with the iterative procedure. The algorithm of the secant method, it is very much similar to the false position method. We will read the initial interval x 1 and x 2, and we will calculate the value of function at these 2 points, and that will be y 1 and y 2. Using the linear approximation, what we will do, we will calculate x 3 by using linear approximation equation of line. You can see on your screen the value of x 3 is calculated by using this expression. After calculating x 3, what we do, we calculate y 3 corresponding to x 3, and now we have a very simple logic. We will calculate the error, and then we go for checking the error. If the error is greater than epsilon, then the next interval is very simple. It is rather far simpler than the false position method. We need not to do anything. What we do, we just say that the previous value, the first value of x is discarded, and the recent 2 value of roots are taken as the next interval. So, what we do, we say x 1 is equal to x 2, correspondingly y 1 is equal to y 2, and x 2 is equal to x 3. X 3 is newly calculated value of root, and corresponding y 2 is now y 3, and we go for repetition. We go to the iterative procedure to calculate the root again. So, the procedure is repeated till the absolute value of error becomes rather relative. We are calculating relative error. Relative error becomes less than epsilon, the allowed error. Now, in this method, as we have already discussed, there are advantages. The advantage is that the convergence is better than successive approximation as false position method, and the computational efforts are less than Newton-Raphson method, although the convergence is slightly less than Newton-Raphson method. So, this method is a better alternative for both false position as well as Newton-Raphson method. In this lecture, we have discussed 3 methods to find root of nonlinear equations in one variable. The first method was false position method, where we were using the linear approximation for the function. The second method was of course a different method, where we were using only one initial guess, and this method uses the approximation for the function as tangent at the given point, at the initial point. The third method is of course an intermediate method between these two, between the false position and Newton-Raphson method, a better alternative for both the methods, and this is the secant method. In secant method, we are also using the linear approximation, and the convergence of secant method is better than false position method, but slightly less than Newton-Raphson method. However, the computational efforts in secant method are less than Newton-Raphson method. So, it is a better alternative for both the methods. Hope you enjoyed the lectures. Thank you.